Good afternoon, everyone. Let's continue with the chapter 2. So during the last week, we talked about the relation algebra operations. So we have these six operations. We have talked about the select. That means select rows. Okay, we based on this sigma, and then in the subscript we write out the conditions. We use a predicate to indicate the condition, and then we can use and or not, like these logic connectors to write a complicate predicate. And then we also talk about the other dimension. So rows we use a select, columns we use a project. So use like this pi, okay, project. So you project along some attributes, list out all the attributes separated by comma. Okay, so like this one. And then we also can have a composition of the select and the projection, so two together. So next one we talk about the Cartesian product, which is this one. So this is the basic one. So in fact we don't use this one very often, but another operation we use that very often, it is based on this one and another operator. So we want to cover this one first. So Cartesian product, so that means we based on the Cartesian space, correct? So Cartesian space, for example, we have a 2D dimension, we use xy. So like this one, 3D, we use xyz. So this is Cartesian geometry. Okay, we use a Cartesian product, means write out like this one, like a multiplication, really like a multiplication, but not really we can do multiplication because we do records, correct? For example, left, right, we have two tables, and then each table have one row on the left, each table have rows on the other side. So in fact, for the Cartesian product, we just do the mapping. For every row in the left table, we map to all the rows in the other table. So if we have m rows in the left table and n rows or n tuples, n records, correct, same meaning, on the right table, then in fact in the end we have m by n tuples. That's why we call it Cartesian product. Okay, so this one allows to combine information from any two relations combine. This combine is really like just like a mathematical combination, not a logical combination. So what it means, so that's why we write out like this. We construct a tuple of the result out of each possible pair. So each possible, that means as long as it comes from left and then one from the other side, so we have a possible combination. Possible maybe it's not logic, means they don't have any relationship. For example, this means instructor teaches. Maybe this instructor does not teach that course, but we still list out that combination combined tuple record. So this means we list all the possible, and then later we can filter out the that means the illegal ones, which is unrelated ones. Okay, so that means we just do a mathematical combination, one from the instructor and the other one from the teachers. Okay, left and the right, okay, we just combine together. So select one and then map all the ones from the right, and then select another one, also map from all the other side. So this is the idea. Okay, so you can find if we do this Cartesian product, we have a big table. Okay, big table. We'll see this one in the next slide. So maybe we have a concern. Okay, so let's look at that table. You can find this one. So instructor, we have the ID, name, and department, and the salary. And then teachers, we have the ID, means the instructor ID, correct? And the course ID, section ID, semester, and the year. So this is for the instructor. This is for the teachers. But you can find here we have two IDs. Two IDs are the same, meaning the name is the same, the attribute name is the same. So we want to differentiate the table, the source, which source, which attribute, which table's attribute, which table's ID. So we can add the table name and then use the period, the domain period, domain operator. So to differentiate these two, because we don't want to mix, because they are not equal to each other, not always equal to each other, correct? So this is the reason. So you can find out this is like the real, just like a rigid mapping. So for each record on the instructor, we match all the record in the teachers, correct? Teachers. Even though this ID is not equal to this ID, we still list them out. So this is called the idea. Okay, called the Cartesian product. Okay, Cartesian product. So you can find that if this one have m, this one have n, we repeat each of these m by n times. So in total we have 1n, 2n, right? And then repeat from 1 to m. So m by n. Okay, so that's the reason. So we want to differentiate, so we can use the name of the relationship. Okay, let's continue. We said that that Cartesian product is not our final target. Our final goal is to want to use another operation called join. And for join, in fact, we also sometimes we call the lateral join. Okay, lateral join. In the previous edition of the textbook, we also use the lateral join. Even now, you still can use lateral join. For here, they are equivalent to each other. So you can use a simple name. Just use join. Join means lateral join. Okay. So the Cartesian product, we associate every tuple of instructor with every tuple of teachers. So that means every. But the problem is that most of the results are not useful because the teacher, the instructor, did not teach that course. Okay, like this one. So this one in fact is like an instructor with ID 12121 teaches the course financial, kind of maybe 201. Okay. So this instructor ID is 10101. So that means even we list this record, but in fact they are not meaningful. Okay, it is not meaningful, all of these things. Okay, so that means we want to filter out those things. We want to only keep those ones which are meaningful. Okay? Meaningful. So this is the idea. You can find out how I filter out. We want to have this one equal to this one, correct? So we keep them. If they're not equal, we'll delete. Correct? Delete. Not equal. Delete. Not equal. Delete. So equal, we keep them. Not equal. Not equal. So that means we will have this. So lateral join or join means they will be equal on the common attribute sets. For example, like this one, the common attribute is ID, correct? Attribute set is only one, ID, only ID for these two tables. So this one appears in the instructor, and also ID appears in the teachers So for others, there's no shared attributes, so you don't need to care. Okay. So for here, in fact, we just based on the Cartesian product and the previous learned selection. Selection means select tuples. Okay. So just like we select along the roads, which one we want to keep along the roads. Okay. So in fact, we first do the Cartesian product, and then we only keep the tuples which are meaningful, means they are equal, they are the same value on the common attribute set. Okay, attribute set. So we can get only those tuples that pertain to instructors and the courses that they taught. So that means it's meaningful. Okay? Only the instructors which have taught those courses or did teach those courses, we keep the records. Otherwise, we just throw away because they are not meaningful. Okay, so the result will be much conciser. You can find it is this one. Okay, they are equal. Okay. Okay. So this is the join. Okay, the join. Okay. Okay, so maybe you also have a consideration. Okay, if they are equal, do we need to repeat this one by twice? Okay, so in fact in SQL we just fit out. Do not need to repeat this one. We only keep one time. Keep the ID value for one attribute and then throw away the other one. And then no need to differentiate whether it's coming from instructor or teachers. So that means that when we implement the SQL, we have some differences. But the overall, that means the basis is still based on the relation algebra. We mentioned the 6 operations explained here. Okay. Okay, this is the join. Okay, the join. And then let's continue. The join operation will allow us to combine a select and a Cartesian. So we know we have that select and then projection, Cartesian join. Okay, Cartesian product. Okay, so this is the join. Okay, the join. Okay. And then if we consider the two relationship R and S. Okay, RS. RS, this means we have a relational schema R and a relational schema S, and then we have a table. So that means that this is the instance of the R, and this is the instance of the S. Okay, we populate the table, two tables with data. And then if we have a predicate theta, okay, we define theta be a predicate on attributes in the schema R union S. Okay, union S. So this means we just have all the attributes, put them together. Okay? So one is R, the other one is S. We combine them together, and then this theta is defined on this attribute sets. Okay, that means it can cover all the attributes which appear in R and both R and S. So the join operation is defined as this. So it's like this one. So it's R natural join theta S equal to sigma theta. Okay, R Cartesian join, Cartesian product S. Okay, so this is in fact just a mathematical description. For example, if we write out the previous example, that one will be sigma instructor dot id equal to teachers dot id. Okay, Of course, that means that this one is a very general one. The theta, this one, in fact, we can define a predicate which is different from this one. Only this one is must be equal on the common attributes. In fact, this one is just like an old attribute set, okay? So this is just like a general one. And then if we said is for short, okay, latch join unit, we said is just like they are equal on the common one. But in fact, for here we can select even further. We may only, for example, for the previous one, we may only just keep physics, keep some computer science, and so on, like this one. So we can add on more, okay? Because the theta will depend on the order attributes, okay? Order attributes, that means union, that means order attributes. So this one is a predicate, but in the minimum, that one will be the common one, right? Just equal to each other on the common attributes. Okay, so that's why we set like this. That's a lateral join. They are equal to each other on the common attribute set. You can also write like this way, because in fact this is a special case of this one. Special case. So you can write this one as this one. Use the join, and then put the condition there. You can use some other, but here it's just equivalent to this one. So lateral join, okay? The lateral join. So they are equal. Put this condition predicate in the subscript of the join operation. Okay. Okay, this is for the join operation. Okay, join operation. So later when we talk about some examples, or we talk about some SQL examples, SQL, when we talk chapter 3, we'll also go back to here, and then this this predicates can be anything, right? So that means that this is join and this is predicate. They're separate. If they are equal to each other on a common attribute set, then we say it's a natural join. Okay, that is a special one. Okay, let's continue for the next one, the union operation. The union. Okay, so union, that means similar like we have two sets. We want to combine the elements in both sets, and then we have a new set which contains all of the different elements in both. So in fact, when we write this one, we can also borrow the definition from the set theory. Okay? R is a relation. S is also a relation or instance of relation. Okay? Is a table. S is a table defined on a relational algebra separately. And then if we combine these two, means first one, because this is a table, okay? This is another table. If we can combine, means they must be defined in the same way, okay? Defined in the same way. For example, this is teachers, these are teachers, these are students, they are students. Okay, they are the same attributes. Okay, same attributes. Let's write out its definition. So that means they have same dimension and the meaning definition. So in fact, for this one, because we define on the set theory, is like you have one set, you have another set, and then you union these two, means you have a new set. Okay, this new set, it contains all the elements either coming from R or come from S. So that means X belongs to R, or X belongs to S. Okay, this is the definition. Okay, because R and S is a set. So for this one, R and S must be the same arity, same number of attributes, at least same number of attributes. That means the size, and then we can just combine the results. Of course, if they are not the same meaning, it's not meaningful, right? Not meaningful. but at least we can have the same columns. If one is more than the other one, how can we combine, right? Okay. And also the next one, the attribute domains must be compatible. Compatible, that means at least they belong to the same region. Okay, same region. For this one is ID, and then this one may be name. So this one is integer, and then the other table when combined also integer. So then they can combine. If one is integer, the other one is string. So how can we combine? That means different meaning. For example, the second column of R, that means the attribute, deal with the same type of values as does the second column of S. Type of value, for this one the same. For example, this is name, this is also name. You may combine some different tables, maybe even represent different objects, but they must have the same number of attributes and the same domain for each attribute. Okay. For example, like this one, to find all courses taught in the fall 2017 semester or in the spring 2018 semesters, in both. So in fact, we can just distill this problem. First one, we want to find all courses either is taught in fall 2017 or taught in spring 2018 or in both. But in fact, either or is already contained in both. So that means for this one, a simple or the easiest way is that you do query on each of them and then combine the result. Combine the result together. So you first find all the courses taught in fall 2017, and then you also find all the courses taught in spring 2018, and after that you combine them together, combine the results together. So that's the result here. So you first find all. So for here, in fact, we only, for example, if we only want to list all the course ID, okay, don't need to care about its other information, names and so on, only the ID, okay, because ID can uniquely define a course. So we look at all the courses in the section table, and then if it is taught in the 2017 fall, so the semester attribute will be fall, and the year will be 2017. So for here, I want to mention, so here is relation algebra. You can find out we use double quotation, means this is a string. But in fact, when we talk about a SQL, in fact, we use only single quotation to represent a string. So do not confuse. Okay. So when we talk about a SQL, we use a single quotation to indicate a string. And then when we talk about the relation algebra, for here we want to differentiate this string, because we're not dealing with programming languages. So we use double quotation to indicate this string. And then semester equal to 4, okay, and use this one, year to 2017. Okay, this means all the courses, you keep all the records, all the courses taught in the 2017 fall, and then you only have interest in the course ID, so you filter out all the other relationships, other attributes. Okay, so this one only select rows, and then you project on columns only the course ID. Similarly, you can just find all the courses taught in 2018 spring, and then filter out, so project on the course ID, and after that use the union to combine them together. So that one will be the courses either in this semester or in this semester. Okay. And then here we give the results. Okay, so that's here, course ID. Okay, you can check the section table and then confirm this one. Let's continue for the next one. So if we have a union, and then we have another one called a intersection. So similar like before, we can write out its set definition. So it's all the elements come from both R and S cut. Okay, so that means the intersection cut. Intersection means this one. This is the intersection. This is R. This is S. This is R. Intersect S. So the previous one will be R O S cut R S. So that's both. Okay, both R and S. Okay, or you can write it like this one. So that one will be here. Okay, this one will be R union S. Okay, so you can fit out this one. So that's the R union S. So similar like before this, we have the same arity and attributes domains are compatible. And then here we do a similar example. We want to find all the courses that are both taught in fall 2017 and spring 2018. So we use similar like before. Okay? We first got the two sets and then we do the intersection. Okay. So we can find only one. Okay? Only one. So for here we need to mention for example, if for this one union. So if CS101 appears in both, then we can only keep one because this is based on the set theory. Is mathematics. Okay? Mathematics. In the SQL, in fact, we can decide whether you want to keep the replicate or not. But in set theory, each element must be different, so we cannot keep them twice. Okay, union will get only one. But when we do the intersection, because this CS101 appears in both sets, and then we'll keep one time only, no problem. And then we find it appears both. It appears in both relation or tables, and then we keep that one time. Yeah, only one time in the resulting table. So you get a CS101. Okay. Okay, this is for the intersection. Okay. And the next one we look at the set difference. Okay, set difference. So set difference means minus. So that means it's appears in one but not appears in the other. That's why we call the set difference. Cat. So this is means X belongs to R and X not belongs to S. So that means all the elements that appear in R but not appear in S, that's we set difference. Cat difference. So all the elements appeared in the R but not appeared in S. So this one appeared in both. Cat in both. So we get rid of this one. We only want to keep this one. Okay? This is the R minus S. This is R intersect S. And then if we use the outside, that's the R union S. So we put them together. Okay? So this is R union S. Okay. Similar like before, same arity and then must be compatible in the domains. Then we can combine. We can do minus as well. We can do this like next subtraction. Find all the courses taught in fall 2017 but not in spring 2018. So it's minus. Okay, so easy, correct? All the courses, okay, in this semester and all courses in this semester, and then show the difference. Okay, show the difference. But this is not equal to S minus R. So the order doesn't matter. Which one appears first doesn't matter. So all the courses that are taught in R but not taught in S, okay, is different from all the courses taught in S but not taught in R. So the order doesn't matter. Okay. Just like 2 minus 4 not equal to 4 minus 2, okay? That's the same reason. So this is R minus S. This is S minus R, okay? So for this one is in the S but not in the R. Okay. Okay, and the next one we have assignment. So in fact, assignment is just want to temporarily rename a temporary result. To give a name to a temporary result, because later you may use this temporary relationship to do further operations. So this is the reason. So it is convenient at times to write a relational algebra expression by assigning parts of it to temporary relation variables. Though you can just union these two together, but maybe it's sometimes it's very long. So rather than write too many things together in one predicate, you can just separate them from each other and then write one first, one component and the other component, and then simply it's just union. Okay? That will be easy. So use assignment. If you generate a temporary result, want to refer to it later, you give a new name, use assignment, use the left arrow. And then sigma department name physics. So just find all the physics instructors, okay, all the physics instructors in that instructor table. And this is find all the music department instructors, and then you will just union means you combine these two together. That means find all the instructors coming from physics or music, or just all the physics or music instructors. Okay, find all instructors. Okay, missing S in the physics and music department. This one double quotation. Okay. So with this assignment, a query can be written as a sequential program. So that means you can do one thing by one time. Okay. So step by step. A sequential program consists of a series of assignments. So just temporarily you get X, you get Y, you get Z, and then you may get a final result is maybe X. Similar like previous, okay? Like this one. Okay. So a series of assignments, okay, followed by expression whose value is displayed as the result of the query. So based on this query's result, you do a assignment again finally. So next one we want to talk about the rename operation. Rename operation is different from previous one. Different is assignment. Give a name, or just like give a name to a relation, to a temporary result. So here, in fact, maybe you will do join to a table itself. So we want to differentiate the left one, the right one. Okay? So we want to give a new name to the name itself within a table. We want to join itself. So you want to differentiate, this is left one, this is right one. So you can give a new name. Okay, this is T, this is P. Right? So then you will know, even they are the same tables, but you refer them in different ways. So this is called a rename. Okay. So the rename operator will use the row. Okay, relational algebra expression do not have a name that we can use to refer them. Okay, so we can use row. Okay, row for that purpose. So that's to complement this thing. The relational algebra don't have this one have a name that we can use to refer to the result. So we can just refer to the result based on the rename. So for example, like this expression row x e means we want to rename e to be x. Okay, that's why we write like this one, e to be x. Do not confuse. Okay, e is the input. Okay, we write it into the parentheses, means that input. This is the result. We don't want to use assignment, so here just means a new name. So give e a new name to be x. Okay, and then we also have another form for the rename, that means even more detailed. So for the e, so for the e, if we assign this one to be a new name x, but at the same time we also want to rename its attributes to be a1, a2, an, then we can write out like this way. Of course, if you still want to use the previous attribute name, you don't need to do this. You can use this one. But if you want to give a new attribute name, you can just write like this way. Right? Give new names for the attributes as well. So that means totally you can change. Okay? You can change the definition. The E table will become A1, A2 till AN table. And for this table, we have new name called X. Okay. And then next one, we talk about the last one. You call it equivalent queries. This means we may perform different queries, but the results are different. We perform different queries for the same problem, but the results are the same. Then we said always the same. Okay? Then we said these queries are equivalent queries. So that because we can solve a problem based on different solutions, this is the same idea. So you need that more than one way to write a query in relational algebra. For example, we want to find information about courses taught by instructor in the physics department with salary greater than 90K. So information about courses, okay, courses taught by instructors in the physics department, with salary greater than 90K. Okay, 90K. Okay. So basically, for here, we want to, in fact, the first one we want to do the first step is about we want to filter out the instructors in the physics department whose salary is less or equal to 90K, correct? Less than. So that means, of course, this one has not finished all the results. In fact, it only find the instructors, correct? So and then maybe later you need to join with the courses, and then because maybe for here you cannot find the course information, only instructor. But here we need to do this step anyway, correct? And then you will do the natural join and so on. But doesn't matter. We don't need to care about that part. We only care about this one. So for this one, when we select the instructors in the departments of physics department, we have two ways to do that. We can first filter out all the instructors. We don't care about whether it comes from physics or not. Filter all the, okay, this is should be a comma. So we filter out all the instructors whose salary are less or equal to 90K. So this is the first operation. And then we only care about the physics department, so we do another selection again. So we first select those rows, and then from these rows we do a final refinement. We only keep the physics, okay? And for this one, in fact, we do two loops, two times refinement or just selection, and this one we do only one time. So for each record, we look at both the department name and the salary. Okay, we look at these two. So department name must be physics, and the salary must be 90K. So we care about both. So for the other one, we only first look at the salary, and then we look at the department name. So in fact, the results are the same. You can just easily find the logic, right? Because they must meet the both selections. You can just fit out the record based on the first selection, first condition, and then fit out again based on the second condition. Or you can do both, right? They're the same. So these two queries will give you the same results. That means that they are not identical. The queries are not identical because you can find that we got a different results, intermediate results in between, right? But they are equivalent, means they have the same results. They can meet the purpose for the same problem. Okay. So we said they are equivalent. Equivalent means they always generate the same results for any database, any instance, database instance for this university database. Okay. Similarly for the other one, okay, we want to find information about courses taught by instructor in the physics department. We can also do like this way. Query 1. You can find this. We do a lecture join. This is really lecture join because the instructors teaches they share only the ID, and then so that means instructors teaches. So that means we join lecture join. We person join these two tables based on this condition. So that means we find out all the instructors who teach some courses. Teach some courses. It can be one or can be more than one. And then we filter out others. Only keep the instructors coming from physics. Then you can get all the information about the courses. About courses. Of course, you can do further. This one contains more than enough information. If you only want to have the course ID, you can do a projection, right? Or name. So you can do a projection by this one, and then doesn't matter. But this one, we just want to see the temporary result are the same as well. Let's look at the second one. So this one, we first do a filter on the instructors. We only need to care about the instructor coming from physics, so we can do this one filtering first, and then after we get all the instructors from the physics department, we can decide whether some instructors will teach some courses. If they teach some courses, we keep those related records for the join. If it's not, we don't keep them. So that's the idea. So we first do this one. All the instructors, all the physics instructors, and then keep all the physics instructors who taught some courses, who are teaching some courses. So this is a lecture join as well. Instructor ID, teacher ID, same as this one. Okay. Of course, I can say this one is quicker, okay, than this one, because you will filter out some unnecessary ones first, make a small table, and then do the lecture join. This one will generate a big table and then filter out, so it's a waste for many of them. And like this one of course is quicker, okay? this one is quicker because you can just do one scan, and then this one need to do 2 scans. Okay, so that's why we want to have query evaluation. Query evaluation, we want to evaluate which one is the most efficient, and then we select that one. So we have evaluation plan and execution. Okay, so these are all the contents we want to cover in the chapter 2. So basically this is about the relation algebra. We talk about the concept first. Okay, so about the relational model first, and then this is called about the attributes in the columns and tuples on the rows, and then we defined some terminologies: attributes, relational schema, R, and then we have instance that will be table, right? And then we have tuples, and then we have each attribute has a domain. So each attribute domain is atomic. So each attribute is atomic. That means each attribute is atomic, means they cannot be further divided into smaller into other attributes, and then now becomes the legal value for every domain. So order does not matter for a table because it's a set. And then we have the database schema, means the tables definition, and the instance means the data populated the tables with data. That's the instance. And then we define the primary key. So we define the super key first, and then that means that as long as you can uniquely decide tuple, that's the super key. If we can select this one, but it also minimum, that one is minimum, that one can be a candidate. If we select the candidate to be the key, that one will be the primary key. And then we also talk about the integrity constraints foreign key reference. So that means not the key of the current table, but its key is the primary key of another table. Then we have a referencing relationship. Okay, like this one. And then we talk about the relational query language, but the most important is the relational algebra one. We want to talk about this one. We involve these 6 basic operations. So all others can come from, like intersect, can be coming from union and set difference. Okay, and the lateral join come from the sigma and the project. Okay, so select, project, union, set difference, Cartesian product, and rename. Okay, lateral join come from Cartesian product and the select. Okay, and then the content we just finished. Cut this sense different. So most important one, of course, is join. Okay, join, select, and project. These 3 are most commonly used. Okay, so just review them and then finish your homework. Okay, I think until now you already be able to finish all the homework 1 questions. Okay, let's first release this one and then continue with chapter 3, which is the sequel.